So at the end of the last video, we looked at trying to find which of these two regression lines was the best fit for this particular set of data. And we found line B was the best fit because it had the smallest summation of the E squares, meaning it had the smallest errors. You can go back and look at the end of that. I don't have the values in here now. But that was only, B is only the best, is just better than line A. It is not necessarily the absolute best regression equation for this set of data. Finding the regression equation for the set of data is what we're going to do in this particular video. So to do that, we need to start looking at our formulas. So the formulas we're going to start with are SXX, SXY, and SYY. These are kind of just they're kind of computational intermediaries, and they don't have any direct interpretation on their own. But S of XX, for example, is simply the difference between each X value and the mean X squared. XYY is the summation of the differences between each Y value and the mean of Y squared, and so on. But they become incredibly helpful. On a test, for example, I will give for you to help with your calculations all of these summations. I'll give you the values of these summations that will allow you to easily find S of XX, XY, and YY. So why do we need those? Let's take a look at our formula sheet for a second. So the formulas I just had up were from here, okay? In me giving you the summations that I'll show you in a minute, and you can calculate these values, you can see you can then use those values and the summations for a lot of the other formulas that we're going to do in this chapter. Okay, so let's take a look. And here is the rest of the formula sheet. So to get our regression equation, we have a formula for slope, S of xy over S of xx. We also have a formula for the y-intercept, b sub o. Okay? And so let's get started. So again, for those of you that have a graphing calculator, you are going to easily be able to put the x values into your list 1, the y values into list 2. So put these as list 1, put these as list 2, and then if you go to stat, calculate, and choose 2 variable statistics, you will get these summations, which again will prove very helpful. You will get summation of x, it's 117, summation of x squared, 1869, so everybody write these down. Summation of the y's is 660. If I were to square all the y's and then sum them, I would get 54,638. And then this summation, and this means I would multiply each x and y together, then add them up. I would get 9,519. So these will be given on a test. From there, what you're going to be asked to do is find xx, xy, and yy. And we can do that right now. So go to your formula sheet, and I'll do xx with you. Then you can try xy and yy on your own. So for xx, it starts, take a look. Don't worry about this first part. That's using each individual data value. You don't want to do that. You want to use the summation. So we need summation of xi squared minus the summation of xi, the whole thing squared, over n. Oops, lost my place. Hold on. So, the summation of xi squared is 1,869. Now, the summation of x, that squared, you have to first put down the summation of x, which is 117, square it, and divide by n, which is 8. If you calculate that, you should get 157.86. For xy, you're going to take the summation of xy, which is 9,519, minus summation of x, times summation of y, the 660, divided by 8. Please work that out, and s of xy is negative 133.5. S of yy is going to be the summation of y squared, that's the 54,638, minus the summation of y, that quantity squared, so that's your 660 squared. Please make sure you know the difference between these. Divided by 8, and that one is going to give me 188. I want you to take note for this, the only one that could end up being negative is your xy value, your s of xy. That is also going to correlate to the slope. So if this is negative, that means you're going to end up with a negative slope, for example. Okay? Once we have those values, so that would be a question on the test, would be to get these values. Then, to get our regression equation, which is b sub o plus b sub 1x. Just like when we do regular linear equations, you're going to find that slope first. So let's take a look at our formulas. The slope is your s of xy divided by s of xx. Sorry, it flips on me every time I do that. So the slope is s of xy, the negative 133.5, divided by s of xx, 157.86, and you should get a slope of negative 0.846. Let's just round 3 decimal places. Now, for b sub o, I'm going to use the 1 over n. And since I have the summations, it's the summation of the y. You can use the other formula if you have your x bars, or you can quickly find your x bar and your y bar from your data. Minus the slope itself, which is negative 0.846. And then that was multiplied by the summation of x's, which you can get off the formula sheet, and that we have over here is 117. So again, if I give you all these summations, you calculate these s values, you'll have no problem plugging everything into the formula, and our b sub o comes out to about, I believe it's 94.867. This gives us our regression formula of 94.867 minus 0.846x. So not quite the same one that we found up here, which was 96 minus 1x, but not too far off from it either. And this is the process you're going to use to find that regression formula for all of your, for any of the problems you're going to do. You can also use StatCrunch when you're doing the problems in MATLAB. If you click Stat, Regression, and then choose Simple, you just select the column that your X values are in, select the column that your Y values are in, and you'll get a printout with a lot of this information on it. So this is not really the best representation because clearly we should be going to 94.867 and this one is not quite going up there. But if you do any of these problems in StatCrunch, you do have the option of choosing your graph so you can see what the scattered points look like along with the regression line. So just some more definitions before we finish this video off. Your predictor variable, I've used that term already, that's your X value. Okay. That's the variable you're going to use to predict or explain the values of the response variables. So in the problem we just did, that was the number of hours that you study, and the response variable was the test grade. That's also kind of your outcome. One of the things I want to talk about also is this idea of influential observations. Okay, so in green we have a set of data that is representative, I believe, of the original data. Let me go back to the beginning for a second. Let me scroll back. Nope, I don't have it on here. This set of data represents the age a car is and the cost of that car. Okay. And as you can see, we have two different regression lines. So the blue line represents using all of the data involved. Okay. Now, how do you know if a data point, which seems a little far off from all the others, is an influential observation? Well, if you remove that data point and it significantly changes your regression line, like it does here, you can remove the data point and it changes the regression line, then it is an influential observation. And influential observations can certainly, researchers can choose to remove those because they feel they get a more accurate regression line if that is removed. And the last thing to keep in mind when starting any sort of regression analysis is before finding a regression line, you actually need to have a scatter plot. And you need to look at that scatter plot and determine if those points appear to be scattered around an actual line. If you don't have that, then you should not move forward to finding that regression line. Right? So you should be able to go through your work in 14.1 and 14.2.